Okay. So I think Deepak also attended. Okay. So in that case, let's continue. So applications of partial differential equations. So the partial differential equations, it has infinite number of applications. So at many places, wherever there is an involvement of fields, so you can find out the application of partial differential equations there, right? Now, keeping that in mind, so we will be discussing only few generic cases wherein these partial differential equations are very widely used. So those are, one is the heat equation, so wave equation. The second one is the heat equation. The third one is Laplace equation. Alright, so these are the standard form of the differential equations. So here, this wave equation, heat equation, and the Laplace equation. So here actually both are, so this is dependent on space and time. So this one also, it depends on space and time. And the Laplace equation, it depends on space. So this is del square phi equal to 0. So this is what is the Laplace equation. So here, Laplace equation is nothing but dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square equal to 0. So this is the Laplace equation. And then the wave equation is dou square phi by or dou square u by dou square y by dou x square is equal to 1 by c square dou square phi by dou t square. So this is the wave equation. So here there is a space dependence and there is a time dependence for the moment of y, and this is one. And another is, so dou square y by dou x square is equal to 1 by c dou y by dou t. So this is the heat equation. Got it? So these are the three different important equations which we are going to discuss as part of the applications of the differential equations. Got it? Partial differential equations. Now in that, so for all the three different equations, we will be adopting a simple procedure. So assuming that the equation is variables are separables, with that assumption actually we will form an equation and then I will try to bring the solution in an easier manner. So first of all, for any generic differential equation, we can think of this kind of procedure. Now let us take the wave equation and then try to solve it. And this is a common procedure for whatever may be the kind of equation it is, whether it is a wave equation or the Laplace equation or the heat equation. The procedure is exactly same. Now just take down this. Okay. Yeah, dou square y by dou t square is equal to c square into dou square y by dou x square. Dou square y by dou t square is equal to c square into dou square y by dou x square. So this is one dimensional wave equation. Now let us say, suppose there is an instrument, a sound instrument. So let us say it's tied up at two different locations, and then this is the length of this string. Now this length of this string, initially it is stretched in this particular format and left it. Suppose you drag it like this and left it, then it will continue to oscillate like this, right? Correct or not? So now the solution of the wave equation is nothing but finding out the displacement vertically at any location of x, and time. So this is what is nothing but the solution of the wave equation, right? So you should be able to find out at this random location x, if you select it, there actually how much it is getting displaced, and this displacement is not constant with respect to time, because at this point of x, so this is continuously oscillating like this. That means at a certain location and at a certain time, you should be able to find out the displacement in the y direction. So that's what is the wave equation, dou square y by dou t square is equal to c square times of dou square y by dou x square. So this is the displacement y. Now initially, if you notice the initial conditions for this, because the solution of the partial differential equation is dependent on the initial conditions here. Now the initial conditions understanding is very much needed. So that understanding is, this is tied up at both the locations, and the displacement is always 0 at this location and is always 0 at this location. That means y is the solution. So y of x comma 0, sorry, y of, so 0 comma t is equal to 0, and y of L comma t is equal to 0. That means irrespective of the time, at the location of x is equal to 0, the displacement is 0, and the location of x is equal to L, the displacement is also 0. So this is two important initial conditions that you have to be aware of it. That is one thing. And another thing is, initially when we give the initial displacement, that means you have dragged the string like this and left it. Now if you drag the string in this particular format and left it, initially before leaving that string from your hand, it is assuming certain shape like this. So this is usually y of x comma 0 is sin pi x by L. So usually this is how actually it will be given, which is nothing but the initial displacement or initial shape of the curve before leaving to vibrate is given as one condition. So this you need to understand. And one more important boundary condition in this is, that is initially so there is no velocity dy by dt equal to 0 at t is equal to 0. dy by dt at t equal to 0 is equal to 0, because there is no initial velocity, because you left like this and without leaving you are holding. That means at that point there is no displacement or there is no velocity in the direction of y. So these are the four important boundary conditions you have to be aware to solve the wave equation. Got it? So this is by common sense also you can make out. So this location and this location there won't be any vertical movement. So that is always fixed, y of 0 comma t and x comma t is always 0. And another is, initially the vertical velocity is going to be 0, that is dy by dt at t is equal to 0 is 0. That is one thing. And initial displacement shape, whatever you have assumed, is given this way. This value is at any instant of, at any value of x, but at time 0 is given as sin pi x by L. So that is one shape. That sin pi x by L can be any value. So usually that depends on the person who is meeting that. Got it or not? Now for this kind of differential equation, whether it is a wave equation or a heat equation or a Laplace equation, usually the methodology what we are going to adopt is, so assume that the solution is to be product of y is equal to x of x into t of t. What it means for us is, so let the solution is a product of two different functions. One is completely depends only on x. And another t is completely depends only on t. On t. So this function is dependent only on t, this function dependent only on the x, and the product of this is coming out to be the solution of the differential equation. That means what we are assuming here it is this particular differential equation where the variables are separables for both the variables t and x. So in this particular differential equation, if this is the solution, then actually we'll try to substitute those values in this and then try to find out the solution based on assuming that this kind of solution will fit for the differential equation like this. Got it or not? This is the standard methodology what we are going to adopt it. So because this is very, very complex level of differential equation to solve. So that's why we start from the solution and go back try to fit into this differential equation. Now, if you put it this way, this is y dash is nothing but y dash is equal to, so y dash we mean dy by dx. So dy by dx is equal to x dash into t, because it is independent of t. This particular function is independent of t. And then d square y by dx square is equal to x double dash into t. So this d can be replaced with dou also. It will not make any difference, because this is completely dependent on x and this is completely dependent on x. That means for all practical purpose, when you are taking the derivative, you can treat this as independent. When you are taking the derivative with respect to t, you have to treat this x as independent, because these two are exactly same. So dou square y by dou x square is equal to x double dash into t, and dou y by dou x is equal to x dash into t. Similarly, dou square y by or dou y by dou t is equal to dy by dt is equal to x into t dash. Similarly, dou square y by dou t square is equal to, so d square y by dt square. So this is equal to x into t double dash. So these are the fundamental equations which will govern the differential equation. Now, if you replace this into the original differential equation, then what you are going to get it is, that is x into t double dash is equal to c square into x double dash into t. Got it? So, or else actually t double dash divided by t is equal to c square into x double dash by x. X double dash by x. Now, let us say I bring this to here, c square, and then this actually I call as a ratio, let us say k. So this ratio, if you separate it, t double dash by c dash, c square t is equal to k, x double dash by x is equal to k. Now, two different sets of solutions. One is completely dependent on x, one is completely dependent on t. And once we solve these two differential equations, we will put back into the original equation, which will give y is equal to x into t, which is nothing but the solution for this differential equation. Got it or not? So the methodology what we have adapted here it is, so you have assumed a solution which is nothing but the product of two different functions which are independent to each other. And based on that, we brought the conditions so that it will satisfy the original equation. And this original equation is nothing but the solution for this. Got it or not? Understood? Or do you have any questions on this? Understood? Deepak, Liju? Any questions on this? Okay, great. So once you got this one, then actually we'll try to solve that differential equation. Now this is as if like it is ordinary differential equation. So you don't need to worry about the partial differential equation at all, because t is completely dependent on t and x is completely dependent on x. That means it will not make any difference whether it is an ordinary differential equation or a partial differential equation. Yeah. So it is always possible to write. For this kind of equations where the higher order differential equations are there, but actually there are no constant functions. Earlier actually quasi-linear equation, if you can think of, that is capital P into small p plus capital Q into small q is equal to R. Now here this R factor will not allow us to find out a solution which is the product of these two. If this R factor is not there, then actually you can think of this way. Got it or not? So here for higher order differential equations, actually this is the standard methodology which we are going to put in. So there are limitations for this as well, right? Where this is possible in this particular case of heat equation, wave equation and the Laplace equation, this is the standard method which was proved to be exists for all kind of waves and all kind of heat equations and all kind of Laplace equations. So that's why actually we use this. So dou square y by dou t square is equal to c square. So this is coming out to be this one. Then t double dash equal to c square t into k. And then t double dash minus kc square t equal to 0. This is one equation. And another equation is x double dash equal to kx, or x double dash minus kx equal to 0. Now here let k equal to p square. So this p square is always a positive value. Then if you put it here, then t double dash minus cp square into t equal to 0, and x double dash minus p square x is equal to 0. Now, so these two we can solve as if like ODE, ordinary differential equation, as it is completely dependent on only on one variable, right? So here it is x and here it is t. Got it? Just a minute. Okay. So now actually this is auxiliary equation to solve this differential equation is, this is m square minus cp whole square equal to 0, or m is equal to plus or minus cp. So the solution for this particular equation is, this is c1 sin cpt plus c2 sin cos cpt. So this is the solution. So which is nothing but the solution for this differential equation, which is equal to t. And similarly, for this equation, the auxiliary equation is m square minus p square equal to 0. Then m is equal to plus or minus p. And then the solutions are going to be, now here it is, so x is equal to c3 sin px plus c4 cos px. So this is one solution which is completely independent of t, and this is one solution which is completely independent of x. So the product of these two, which is nothing but the solution y is equal to x into t is equal to c3, or actually I call this as c3 and this as c4 and this as c1 and this as c2. That is, yeah, so xt you can put it as c1 sin px plus c2 cos px getting multiplied by c3 sin cpt plus c4 cos cpt. So this is the solution of the differential equation. Got it? So here actually there is one important conclusion. Sorry, actually the solution is going to be not this way. So this is c1 e power cpt plus c2 e power cpt, and then c3 e power px plus c4 e power minus px, minus cpt. So the product of these two will be the solution, as long as if you have the solutions are plus or minus p here and plus or minus cp here. So here the roots are real and unequal. So I hope you are aware of the fact that in case of ordinary differential equations, once we find out the auxiliary equation and solve for it, and the solutions whatever you are going to get once we solve the auxiliary equation, suppose those are real and unequal, then actually, so this is the kind of solution we are going to get. So this is xt value, which is nothing but y. So this is one kind of solution. Suppose if the roots are complex conjugates, then this is the solution we can expect. Now in this case, here actually k is equal to p square, which is nothing but always positive value we have assumed. If it is always positive value, then this is the kind of solution you can get it. And then suppose if I say k value is going to be minus p square, then So here actually this value is coming out to be plus and this is also coming out to be plus. Now the roots are going to be complex conjugates, plus or minus ICP and plus or minus IP. So in such cases, this is the solution you are going to get it. Got it or not? Understood? Is this understood? Deepak? Any questions on this? So another case is when P equal to 0. That is the third case. So when P is equal to 0, this is straight away like, so just this is 0 and this is also 0. 2 times integration of this, so you are going to get one solution. Now, out of all the 3 different solutions, where this K value, whatever you have taken as the ratio, if it is positive, then this is the solution. If it is 0, then you are going to get a solution with X and T. And then if it is negative, then you are going to get the solution like this. Now, because we are solving a wave equation which has to involve the coefficient of sines and cosine, so out of all the 3 possible solutions, only one is the appropriate solution for us. That is this case where this K value is going to be negative. Got it or not? I need response from you. Deepak and Liju. Understood or not? Okay. So once you understand this one, so now actually we have concluded that, so this is the appropriate solution which you can pick up to solve our wave equation. So this is ruled out and K is also ruled out. Yeah, so I am going to solve anyway this kind of problem. See this. Alright, so I just repeat this solution so that you can get a better clarity. See this. Till this point, did you understood? Deepak? Is this understood or not? Till this point, assuming that it is a product of the solution. Now actually this differential equation actually we are trying to fit into back here. Now if you fit it, then actually one solution is T square is equal to KC square T. And another solution is X double dash is equal to Kx. So X double dash minus Kx equal to 0. So here T double dash minus Kc square T equal to 0. Now this K actually is a ratio we have assumed. And then 3 different cases we will analyze. One is K equal to 0. Another is K is positive. Another is K is negative. Now the first case K is 0. Let us say. If K is 0, then case 1. So T double dash equal to 0 and X double dash equal to 0. And then here, if you take one integration, then this is going to be, so this is a constant, C1. And then if you integrate again, T is equal to C1T plus C2. So this is one solution. Similarly, if you integrate once, X dash is equal to C3 and X is equal to C3X plus C4. Now the solution is Y is equal to XT, which is equal to X is C3X plus C4 and C1T plus C2. So this is one solution. Got it? If K is equal to 0. This solution understood? Yes or no? So this is one solution. Now one more solution, assuming case 2. So case 2, let K is positive. If it is positive, then T square minus, I call this as, which is equal to K is equal to P square I call. So assuming that P is always positive, right? Obviously if I take P square, it will be always positive, P square value. So K can be treated as P square and then C square T equal to 0 or T double dash minus Cp whole square T equal to 0. And here also X double dash minus P square X is equal to 0. Then the auxiliary equation is going to be, this is M square minus Cp whole square equal to 0. And then here also M square minus p square is equal to 0, or m1 I call, this I call as m2. Then m2 is equal to plus or minus cp. Yeah. And here m1 is equal to plus or minus p. So for this actually, if the auxiliary equations are solutions of this one, then the complementary function is nothing but the solution. The complementary function is going to be c1 or c3 e power cpt plus c4 e power minus cpt. So this is the complementary function. Similarly, for this, the complementary function is going to be cf is equal to, so c1 e power px plus c2 e power minus px. So this is the complementary function. So because actually on the right hand side it is equal to 0, so we can find out only the complementary function. There is no need of finding out the solution for it. So there is no need of finding out the particular integral because the right hand part is 0. And similarly, yeah. So if you take out the second one, so that is the case 3. Suppose if the case 3 value, let k is negative, that means minus p square. If k value is minus p square, which you can say it is always a negative number. So if it is a negative number, then you can put it here t double dash, then k is minus p square, then this is plus p square c square t, and here also x double dash minus of minus will be plus p square x equal to 0. So this is t double dash plus pc whole square t equal to 0, and x double dash plus p square equal to 0. Then the auxiliary equation is going to be m1 square plus pc whole square equal to 0, and m1 is equal to plus or minus ipc, and here m2 square plus p square equal to 0, and then m2 is going to be plus or minus ip. So then the complementary function is going to be cf is equal to, so here c3 sin cpt plus c4 cos cpt, and this is the solution when the roots are imaginary. And then on the right side also, here the complementary function is going to be c1 sin px plus c2 cos px. So this is the solution. Now the complete solution is going to be the product of these two, because which we have assumed the initial solution as for this one xt, y is equal to xt. Got it? So we have got 3 different solutions for 3 different values of k. So if k is equal to 0, we have got c1x plus c2 times of c2t plus, c3t plus c4. I'll just write down all the 3 different possibilities. So note it down. Noted or not? Now, all the 3 possible equations are so here in this case actually, in this particular case actually we don't have the possibility of getting the real and imaginary part. If it is having real and imaginary part, the solution will not make any difference. So what you are going to get extra is, suppose if the solutions are alpha plus or minus I beta, then this is e power alpha t times sin beta x c1 times of plus c2 times of cos beta x or beta t. If it is t, then it is t. This is how you are going to get it in case if you get the real and imaginary part. But for in this case, we have got only the real part, hence it is going to be 0 to this point. Yeah, maybe a damped wave, exactly. Got it? So here actually 3 solutions. One solution is c1x plus c2 times c3t plus c4. This is one solution. And the second solution is, this is k equal to 0. and this is k is equal to p square. In this case, what we have got is c1 e power px plus c2 e power minus px times c3 e power cpt plus c4 e power minus cpt. And then case 3, k is equal to minus p square, then this is going to be c1 sin px plus c2 cos px getting multiplied by c3 sin cpt, c4 cos cpt. Now actually three different kinds of solutions we have got. So out of all the three possible solutions, so this won't fit for a wave equation because it is having coefficients which are multiplications of the constants. So the product is no more a periodic wave. Even here also, because these are the real values, so this is also will not fit because this is not going to be a wave equation. So this is continuously increasing or decreasing functions, you are going to get it. So the only possibility here it is, there are some periodic curves that are there. So this periodic curves, right? So which is nothing but the solution of the wave equation. So this will give a form of periodic curve. So the appropriate solution will be this one. So solution 3 is more appropriate. Solution 3 is more appropriate out of all the solutions. Got it? So hence actually we pick up only this particular solution to fit for our realistic waveform. Got it? So if at all he talks about a wave equation, straight away you can pick this. Got it? So if it is a wave equation, straight away you can pick this. From there you can proceed based on the boundary condition. Now let us see what are all the boundary conditions that are there, and then so note down one problem based on this understanding. A string is stretched and fastened. A string is stretched and fastened to 2 points L apart. To 2 points L apart. Motion is started by displacing the string in the form of A sin pi x by L. Motion is started by displacing the string in the form of y is equal to A sin pi x by L. So in this form actually initially it was stretched, from which it is released at time t is equal to 0. It is released at time t equal to 0. So that the displacement at any instant, so show that the displacement at any instant be y of x comma t equal to A sin pi x by L cos pi ct by L. A sin pi x by L cos pi ct by L. So he asked us to prove this. So initial displacement is A sin pi x by L. So that is the initial condition y of 0 comma. y of x comma 0. So this is the initial condition, and 0 comma t is always 0 and L comma t is always 0, and the initial velocity dy by dt at t is equal to 0 is again 0. So based on these conditions, we have to be identifying the wave equation to be this way. Got it? So now actually initially we assume the solution. So the solutions is, so let the solution of the wave equation is y of x comma t. So this is the fundamental solution, is coming out to be c1 sin px plus c2 cos px multiplied by c3 sin cpt plus c4 cos cpt. Got it? So this is the solution. Now we'll try to substitute one by one the initial condition. So the first initial condition is y of 0 comma t is always 0. This is the first initial condition. If I put the value x is at 0 and t value as it is, then c1 into 0 plus c2 plus c3 sin cpt plus c4 cos cpt. So this is 0. So here this is coming out to be c2 into c3 sin cpt plus c4 cos cpt. Now this will be 0 if ct equal to 0. Correct or not? So because this is independent of x, so the only possibility is c2 can be 0, so that actually this part as it is, it can be there, and then the result has to be 0 because the initial condition is y of 0 comma t is equal to 0. So c2 equal to 0, and then the solution is going to be, now actually y of x comma t will be obviously, so this is c1 sin px getting multiplied by c3 sin cpt plus c4 cos cpt. So this is the equation, and then another condition is dy by dt equal to at t is equal to 0 is 0. That means if I put that dy by so if you take the derivative of this, so dy by dt is equal to c1, so with respect to time, sin px as it is, and then c3 times of derivative of sin cpt is cp times of derivative of sin is cos cpt. So derivative of cos is minus sin cpt, and this value is coming out to be 0 at t equal to 0. See, if I put t is equal to 0, this part will be 0 and this part will be c1 sin px getting multiplied by c3 cp cos cpt. So this part is anyway 1 because at t is equal to 0. So this value is coming out to be 0. So this is possible only if c3 equal to 0 but not c1. Why? Because at L also it will be another condition. So we have taken this as the first condition, this as the second condition, and the third condition also I am going to take it up that one. Now here, so note this point. So here actually C3 will be 0, but C1 will not be equal to 0. Why? Because if C2 0 and C1 is also 0, then actually this product will always be 0. Hence, that will be a trivial solution for us. Got it? So hence, you should not treat C1 equal to 0. So there is only one possibility, C3 equal to 0 in that case. Got it? Understood or not? So if I replace C1 is equal to 0 and C3 is equal to 0 in the original equation, the remaining equation whatever we are going to left it is, that is, so here, so based on the other condition, we have got the C3 is also 0. That means whatever is left over is C4 cos CPT. So this is y of x comma t is equal to c1 c4 sin px cos cpt. So this is the solution. Now the simplest solution we have got. But actually still the unknown constants are c1, c2 are there. Now c1, c2. So take the other condition, that is y of L comma t, if you take it, this is always 0 irrespective of the time. So c1, c4 and sin PL cos CPT is always equal to 0, right? So here this is the condition. If this has to be 0, then one node has to happen at this point, which means sin PL can be 0. So sin PL is equal to 0. And if this is 0, the solution, general solution of sin is sin n pi. That means PL is equal to n pi, or P is equal to n pi by L. So this is another condition. So if you replace it here, y of x comma t is equal to c1 c4 sin n pi by L, n pi by L into x cos nc pi by L into t. So this is the solution, right? Yeah, so product of these two arbitrary conditions is again one more concept which we are going to find it out now. Got it? Now actually one last condition, that is the initial condition what we have given is y of x comma 0 is equal to sin pi x by L. That means if I substitute here, then at t is equal to 0, the initial condition is, if you substitute this one, so y of x comma 0 is equal to, so c1 c4 sin n pi x by L into 1 is equal to a sin n pi x by L. So that means, so this a value is equal to c1 c4. So c1 c4 is equal to a. So this is one condition. Now if you collate all the conditions together, we will get only one possible solution out of all the simplified form. That is y of x comma t is equal to a sin n pi x by L into cos of n pi c t by L. Got it? So this is the general solution. Now this will give at any position x, if you substitute x is equal to 1 or 2 or whatever it may be, you are going to see what is the displacement for any random value of time t. Suppose if you want to find out by fixing one location at any time, so you will be able to find out by changing the time value there. So that means this wave equation is dependent both on x on t. Understood? Got it? Any questions on this? Got it? So this is how actually we will be solving the wave equations. So if you have any questions, you can let me know, or else actually we'll stop for today. Tomorrow actually I am going to take one more problem based on this wave equation, and then we'll continue with the heat equation tomorrow. Yeah. So that's all for today. Yeah, thank you.